Assalamualaikum everyone and a very good day to all. In this video, we shall learn about time division multiplexing or TDM, which is one of the basic techniques of multiplexing. Here is the table of contents for you to navigate through this video. So this video is the continuation from TDM video part 2. In this video, we shall continue to learn about synchronous TDM as well as some of its applications. So let's quickly recap. Multiplexing is basically a set of techniques that allows the simultaneous transmission of multiple signals across a single data link. Whereas TDM is a digital multiplexing technique for combining several low-rate digital channels into one high-rate channel. A particular case of TDM which we are still discussing is known as synchronous TDM. This is commonly used for multiplexing digitized voice streams and data streams. In this figure here shows a conceptual view of TDM. Note that the same link is used as in FDM. Here, however, the link is shown section by time rather than by frequency. In the figure, portions of signals 1, 2, 3 occupy the link sequentially. I have explained interleaving in the previous video, but just to review, we can explain interleaving in synchronous TDM as follows. TDM can be visualized as two fast rotating switches, one on the multiplexing side and the other on the multiplexing side. The switches are synchronized and rotate at the same speed, but in opposite directions. On the multiplexing side, as the switch opens in front of a connection, that connection has the opportunity to send a unit onto the path. This process is called interleaving. The bottom figure shows the interleaving process for the particular connection shown at the top middle of this page. All examples in this video are still of synchronous TDM. Okay, in this example, 4 channels are multiplexed using TDM. The questions are, if each channel sends 100 bytes per second and we multiplex 1 byte per channel, A, show the frame traveling on the link, meaning you have to draw them. B, the size of the frame. C, the duration of a frame. D, the frame rate. And E, the bit rate for the link. We can answer the questions as follows. For A, the multiplexer and the frame traveling can be drawn as shown here. We have 4 channels, then they are multiplexed 1 byte per channel, so each frame traveling on the link will have 4 bytes. For B, as each frame carries 1 byte from each channel, therefore the size of each frame is 4 bytes or 32 bits. For C, the frame rate must be 100 frames per second because each channel is sending 100 bytes per second and a frame carries 1 byte from each channel. For D, the duration of a frame is the inverse of the frame rate, so it will be 1 over 100 or 0.01 second. For E, so just now we calculated the frame rate. How to calculate the bit rate? Just multiply with the number of bits in each frame. Since each frame contains 32 bits, the bit rate is 100 times 32 or 3200 bits per second. This is actually 4 times the bit rate of each channel, which is 100 bytes just now multiplied with 8 to get bits, so it is equals to 800 bits per second. So this is 4 times the bit rate of each channel. Now I want you to try this yourself and see if you can get the answer. Assume that the data rate for each input connection in figure on the left is 50 bytes per second. And then we multiply 2 bytes per channel. Do A to E for the new scenarios. Let's do another example. A multiplexer combines 400 kilobit per second channels using a time slot of 2 bits. The questions are A, show the output with these given 4 inputs. Then find B, the frame rate, C, the frame duration, D, the bit rate, and E, the bit duration. We can answer the questions as follows. For A, the output for the 4 input as shown here. For B, the link carries 50,000 frames per second since each frame contains 2 bits per channel. For C, the frame duration is therefore 1 over 50,000, or you'll get 20 microsecond. For D, the frame rate is 50,000 frames per second, and each frame carries 8 bits. So the bit rate is 50,000 times 8, and you'll get 400,000 bit per second, or 400 kilobit per second. For E, the bit duration is 1 over 400,000 second, or you'll get 2.5 microsecond. Note that the frame duration is 8 times the bit duration because each frame is carrying 8 bits. Now I want you to try this yourself and see if you can get the answer. Assume that the data rate for each input connection in the figure above is 200 kilobit per second and using a time slot of 3 bits. Do A to E for the new scenario. Sometimes an input link may have no data to transmit. When that happens, one or more slots on the output link will go unused. That is wasteful of bandwidth. So as you can see, synchronous TDM is not as efficient as it could be. If a source does not have data to send, the corresponding slot in the output frame is empty as shown in this figure, where one of the input lines has no data to send and one slot in another input line has discontinuous data. The first output frame has 3 slots filled, second frame has 2 slots filled, and the third frame has 3 slots filled. No frame is full. We learn in the next section that statistical TDM can improve the efficiency by removing the empty slots from the frame. Before that, let's look at data rate management. Data rate management deals with how to handle a disparity in the input data rates, as not all input links may have the same data rate. Some links may be slower. There may be several different input link speeds. In all our discussions so far, we assumed that the data rates of all input lines were the same. However, if data rates are not the same, 3 strategies or a combination of them can be used. The 3 strategies that can be used to overcome the data rate mismatch are called multi-level multiplexing, multiple slot allocation, and pulse stuffing. Multi-level multiplexing is a technique used when the data rate of the input links are multiple of each other. For example, in the figure on the left here, we have 2 inputs of 20 kilobit per second and 3 inputs of 40 kilobit per second. The first two input lines can be multiplexed together to provide a data rate equal to the last 3. Second level of multiplexing can create an output of 160 kilobit per second. Multiple slot allocation can be used when there is an input line that has a data rate that is a multiple of another input. The higher bit rate channels are allocated more slots per frame, and the output frame rate is a multiple of each input link. It is more efficient to allot more than one slot in a frame to a single input line. In the figure at the bottom, the input line with a 50 kilobit per second data rate can be given 2 slots in the output. We insert a demultiplexer in the line to make 2 inputs out of 1. Sometimes the bit rates of sources are not multiple integers of each other. Therefore, neither of the 2 techniques mentioned just now can be applied. One solution is to make the highest input data rate the dominant data rate and then add dummy bits to the input lines with lower rates. This will increase their rates. This technique is called pulse stuffing or sometimes as bit padding or bit stuffing. This is shown as in figure on the right. The input with a data rate of 46 is pulse stuffed to increase the rate to 50 kilobit per second. Now multiplexing can take place. Basically, the slowest speed link will be brought up to the speed of the other links by bit insertion. Another issue to be considered with the implementation of TDM is frame synchronization, as synchronization between the multiplexer and demultiplexer is a major issue. If the multiplexer and the demultiplexer are not synchronized, a bit belonging to one channel may be received by the wrong channel. For this reason, one or more synchronization bits are usually added to the beginning of each frame. These bits, called framing bits, follow a pattern frame to frame that allows the demultiplexer to synchronize with the incoming stream so that it can separate the time slots accurately. In most cases, this synchronization information consists of one bit per frame, alternating between 0 and 1 as shown in this figure. Let's continue with another example. We have 4 sources, each creating 250 characters per second. If the interleaved unit is a character and one synchronizing bit is added to each frame, find A, the data rate of each source, B, the duration of each character in each source, C, the frame rate, D, the duration of each frame, E, the number of bits in each frame, and F, the data rate of the link. We can answer the questions as follows. Okay, as you may all be aware, characters are typically of ASCII and its encoding is of 8 bits character. So for A, the data rate of each source is 250 multiplied with 8. So we'll get 2000 bits per second or 2 kilobits per second. For B, each source sends 250 characters per second. Therefore, the duration of a character is inverse that 1 over 250 seconds or 4 milliseconds. For C, each frame has one character from each source, which means the link needs to send 250 frames per second to keep the transmission rate of each source. For D, the duration of each frame is 1 over 250 seconds or 4 milliseconds. Note that the duration of each frame is the same as the duration of each character coming from each source. For E, each frame carries 4 characters and 1 extra synchronizing bit. This means that each frame is 4 times 8 plus 1 equals to 33 bits. And finally, for F, the link sends 250 frames per second and each frame contains 33 bits. This means that the data rate of the link is 250 multiplied with 33, or you'll get 8250 bits per second or 8.25 kilobits per second. Note that the bit rate of the link is greater than the combined bit rates of the 4 channels. If we add the bit rates of 4 channels, we'll get 8000 bits per second, because 250 frames are traveling per second and each contains 1 extra bit for synchronizing. So we need to add another 250 to the sum and you get the same data rate, which is 8250 bits per second. Now I want you to try this yourself and see if you can get the answer. Assume that the data rate for each input connection is 400 characters per second. If the interleaved unit is a character and 1 synchronizing bit is added to each frame, find A to E as from the example above in the new scenario. Let's do another example. 2 channels, one with a bit rate of 100 kilobits per second and another with a bit rate of 200 kilobits per second, are to be multiplexed. How can this be achieved? What is the frame rate, what is the frame duration, and what is the bit rate of the link? We can answer the question as follows. For A, we can allocate 1 slot to the first channel and 2 slots to the second channel. The second channel is with the higher bit rate, 200 kilobits per second. So each frame can carry 3 bits. For B, the frame rate is 100,000 frames per second because it carries 1 bit from the first channel. For C, the frame duration is 1 over 100,000 second or 10 milliseconds. For D, the bit rate is, you can calculate by multiplying 100,000 frames per second with 3 bits per frame. So the frames will cancel out and you will be left with 300 kilobit per second. Note that because each frame carries one bit from the first channel and the bit rate for the first channel is preserved. The bit rate for the second channel is also preserved because each frame carries 2 bits from the second channel. Now I want you to try this yourself and see if you can get the answer. Assume that we have 3 channels, 2 with bit rates of 100 kilobit per second and another with a bit rate of 200 kilobit per second. And they are to be multiplexed. Explain how can this be achieved, then find the frame rate, the frame duration, and then the bit rate of the link. Telephone companies implement TDM through a hierarchy of digital signals, called digital signal service or digital hierarchy. In this figure, we can see the data rates supported by each level. We have the S0, it is a single digital channel of 64 kilobit per second. Next, we have the S1, it is a 1.544 megabit per second service. 1.544 megabit per second comes from 24 times 64 kilobit per second plus 8 kilobit per second of overhead. It can be used as a single service for 1.544 megabit per second transmission, or it can be used to multiplex 24 DS0 channels or to carry any other combination desired by the user that can fit within its 1.544 megabit per second capacity. DS2 is a 6.312 megabit per second service. 6.312 megabit per second is 96 times 64 kilobit per second plus 168 kilobit per second of overhead. The overhead is to provide extra bandwidth for the DS2 bit stuffing and the DS2 overhead bits. The DS2 overhead bits provide alignment and bit stuffing control. The DS2 can be used as a single service for 6.312 megabit per second transmission, or it can be used to multiplex 4 DS1 channels or 96 DS0 channels, or a combination of these service types. DS3 is a 44.376 megabit per second service. 44.376 megabit per second is 672 times 64 kilobit per second plus 1.368 megabit per second of overhead. It can be used as a single service for 44.376 megabit per second transmission, or it can be used to multiplex 7 DS2 channels, or 28 DS1 channels, or 672 DS0 channels, or a combination of these service types. Then we have the S4. It is a 274.176 megabit per second service. 274.176 megabit per second is from 4032 times 64 kilobit per second plus 16.128 megabit per second of overhead. The rate is chosen to provide extra bandwidth for the S3 bit stuffing and the S3 overhead bits. The DS3 overhead bits provide alignment, error checking, in-band communications, and bit stuffing control information. The S4 can be used to multiplex 6 DS3 channels, or 42 DS2 channels, or 168 DS1 channels, or 4032 DS0 channels, or a combination of these service types. DS0, DS1, and so on are the names of services. To implement those services, the telephone companies use T lines, the T1 to T4. These are lines with capacities precisely matched to the data rates of the DS1 to DS4 services, as you can see in this table. So far, only T1 and T3 lines are commercially available. The T1 line is used to implement DS1, T2 is used to implement DS2, and so on. And as you can see from this table, the S0 is not actually offered as a service, but it has been defined as a basis for references purposes. T-lines are basically digital lines designed for the transmission of digital data, audio, or video. However, they also can be used for analog transmission, such as regular telephone connections, provided the analog signals are first sampled and then time division multiplexed. The possibility of using T-lines as analog carriers open up a new generation of services for the telephone companies. Earlier, when an organization wanted 24 separate telephone lines, it needed to run 24 twisted pair cables from the company to the central exchange. Today, the same company, the same organization can combine the 24 lines into one T line, into one T1 line, and run only the T1 line to the exchange. This is as shown as the figure at the top right, where it shows how 24 voice channels can be multiplied onto one T1 line. You can refer to chapter 4 for PCM encoding. We've learned this before. The T1 frame, as noted above, DS1 requires 8 kilobit per second of overhead. To understand how this overhead is calculated, we must examine the format of a 24 voice channel frame. The frame used on the T1 line is usually 193 bits divided into 24 slots of 8 bits, each plus 1 extra bit for synchronization. So basically it is 24 multiplied with 8 plus 1. You'll get 193, as shown here in the figure at the bottom right. In other words, each slot contains one signal segment from each channel. 24 segments are interleaved into one frame. If a T1 line carries 8,000 frames, the data rate is 1.544 megabit per second. You can see that it's the same like in DS1 just now. Okay, this T1 line is from 193 multiplied with 8,000, and you'll get 1.544 megabit per second. That is the capacity of the line. Another application that uses TDM is another version of T-lines, which is used by the Europeans, called E-lines. The two systems are conceptually identical, but their capacities differ, as you can see in the table on the right, where it shows the E-lines and their capacities. Another synchronous TDM application that we just mentioned here is the second generation cellular telephone. For example, the digital version of cellular telephony divides the available bandwidth into 30 kHz bands. For each band, TDM is applied so that 6 users can share the band. This means that each 30 kHz band is now made of 6 time slots, and the digitized voice signals of the users are inserted in the slots. Using TDM, the number of telephone users in each area is now 6 times greater. You can have a read on second generation cellular telephony in chapter 16 in Frozen textbook. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.